We're going to launch into Chapter 14, Nuclear Magnetic Resonance Spectroscopy. This is typically seen by the average person with MRI in the medical field, that is magnetic resonance imaging. So this is primarily used by researchers to study the structures of organic compounds. It looks at the bonds between, it can help you piece together the bonds between carbon and hydrogen. And it's extremely powerful. It was developed in the 1940s to study atomic nuclei, and in the 50s, chemists started realizing that it could be used to elucidate structure. And one of the reasons why it is so powerful is it doesn't just work on carbon and hydrogen. It can work on any element or any nuclei that have an odd number of protons, neutrons, or both, right? And this is because they have a property, these nuclei have a property called spin that allows them to be studied by NMR. So, this hydrogen 1, carbon 13, nitrogen 15, so on and so forth, but not carbon 12 or oxygen 16 or any elements or isotopes that are going to have an even number. Those won't work. And so what happens is, if you can think of these elements, these atoms, these nuclei being spread about in space and not being subjected to a magnetic field. So if I were to draw here a box, right? If I were just to draw a simple box and I were just to have a bunch of these little guys in here, and I'm drawing these arrows for a very particular reason. You have to realize that the arrows represent the spin. So if I have a sphere here, right? Imagine like the Earth. The Earth has an axis and it spins around that axis, right? So here's the direction of the spin, right? So the bold arrow is the direction of the spin, and here's the axis, right? So you would say that this axis would represent the moment. So this yellow arrow is the direction of the spin, and the white arrow is the moment. So what's very interesting is the moment is completely random when you don't have a magnetic field, right? So all of these nuclei have a completely random direction of their magnetic moment without an applied magnetic field. And this is only when they have that odd number of protons, neutrons, or both. However, when they have an applied magnetic field, something very interesting happens, and this is what's here. When you apply a magnetic field, you get a bifurcation, you get a splitting. What happens is you're going to think of being in the ocean, and you're either going to be swimming with the tide or against the tide, right? So you can either be in the alpha state or the beta state. So what happens is you're going to have the magnetic moment either be up or down, right? If you're swimming against the tide, you're going to have a higher state of energy, right? You're going to be using up your energy. But if you're swimming with the tide, you're going to be moving faster and using less energy. So that's the metaphor that we're trying to use here. So the beta state is at a higher degree of energy, and the alpha state is at a lower degree of energy. So all of this is to say, if I were to draw another box here, I'm only going to draw this face here. I'm not going to draw the whole box, and I were to draw the magnetic moments, if there's a magnetic field, all the magnetic moments are going to be in alignment, but you're going to have some that are in disalignment, right? They're against it, but they're going to be far less. And I'm going to explain that in just a moment. So let's go ahead and I'm going to go ahead and pull up my next slide here. So there's something very intriguing here. So as the strength of the think about this, as the strength of the magnetic field increases, as the strength of the magnetic field increases, that energy gap, that gap between the two states, the alpha and beta states, where you have the moment going up or the moment going down, right? Remember, the spin is one direction, but it doesn't really matter. The moment going up or the moment going down, spin up, spin down, whatever, increases. And this is why more powerful NMR spectrometers are sought after, and they're more expensive. This is that's really condensing the story. But that's why every few years you have some research labs, government research labs, the CDC, or R1 institutions are going to have, they're going to advertise, oh, we have, an 800 megahertz or we have a gigahertz NMR spectrometer, right? It's because they have the money for it, first of all, but they have a much higher resolution. They can, they can give a lot better data, and the research will be a lot more clear. So here's the thing. There's a vast excess of protons in the alpha state. This is so here's that drawing that I had. So this was the alpha state, right? And here's the beta state. The beta state was the one that was higher in energy. So if there are a vast excess of nuclei, right? So this should read nuclei, because we're talking about proton NMR. So I mean, yeah, this could be protons, but we should be talking about nuclei. So if there are a vast excess here, then it makes sense. We're going to be pulsing these nuclei, these protons, with radiation to shoot them up to a higher energy state, so that when they relax, they're going to emit radiation. And then we're going to have a detector. A detector, this is an eyeball, right? A detector is going to detect this radiation that is released by the relaxation of the excited, remember this was an excited from the alpha state, the excited nuclei that was in the excess relative ground state. It released radiation to the detector. That goes to a computer, interprets it, and informs our spectra. So if there's a vast excess, there's about 1 million to 20. So there's about 1 million in the alpha state to 20 in the beta state. So that's great. That's great. That's what we want. So we seek to excite the lower state to obtain a signal. And over here, this graph is interesting because it shows us that as you apply more of a magnetic field, you are widening the energy gap. These yellow lines are showing that you are widening that gap. And if you widen that gap, then what is very interesting, if you widen this gap, think about it. If you make the gap wider, you're making it more difficult for for these lines to be blended together, right? So maybe instead of 1 million to 20, you can make it 1 million to 5. You can make it 1 million to 1. So then when we're not talking about 1 million, but we're talking about, 10 to the 23, we're talking about a mole, right? We're talking about moles of things, then we're going to have serious excess, right? So all of this starts to add together when we're talking about efficiency, we're talking about resolution, and we have really complex molecules, we can make out what they are. So this is a very in-depth review, introduction, but I believe it serves you right to understand what's really going on here. So when a sample is subjected to a pulse of radiation, right? So when we're subjecting the sample to a pulse of radiation, and that radiation's energy corresponds to that difference, right? That difference in the energy, in the gap between alpha and beta, right? Those states. Well, what can happen is those nuclei, those protons, they can flip their spin. So this is very similar to when, we've learned about this. If you have an electron and you apply, light to it, and it can jump to a higher higher energy level, and then it's in an excited state, and then it can jump back down and it can release light, right? And that's what happens in the atmosphere all the time, in the northern lights and the aurora lights, right? So we get those beautiful green, blue, purple lights. That's what's happening all the time. This is very similar to that. So NMR spectrometers make use of that, but for the nuclei, and they make use of it by manipulating the electromagnetic principles of light. So that's and nuclei. So very interesting. So this occurs in a decaying fashion over time, and we're not going to go into the mechanics of that because if you're a chemistry major, you will likely learn that in instrumental analysis. So A computer will take that information and it will do something called a Fourier transform, and you can read in your textbook in section 14.2 about this, and it will convert that to the time domain, from the time domain to the frequency domain, and give you your spectra, right, or your spectrum. And that is what you're going to interpret to try to figure out, oh, this is, the molecule I have. Wonderful, great. So, that's how chemists figure out what molecules they have. They interpret their spectra. They have tables of, what should show up at 4.9. And, oh, I know aromatic things show up at 6.8. I know that this shows up around 12. So keep that in mind as you're studying. And I hope this introduction serves you well. The next section we're going to talk about shielding, and I'll see you there. So thanks a lot.